Okay, next up we would like the structure for ICl4- and IF5. Provide the steric number, draw the VSEPR structure, identify the bond angles and name the shape. Identify any distortions in the bond angles due to lone pairs. And so we're going to start with the first one. Begin by counting our valence electrons. So we're going to have 7 from the iodine, plus 4 by 7 from the chlorine, plus 1 because of the charge. So this is going to give us 35 plus 1, and that's going to be 36 electrons. Okay, next up, we are going to draw our structure. We're going to choose I as the central atom. Yes, they both have the same number of maximum bonds, but in this scenario, I can form the expanded octet, and we have more chlorines to put around it, so it makes the most sense. We start with our Cls. And let's begin with a single bond on each and filling in the chlorine's octets. And if we have anything left, then we put it on the iodine. And so we're going to have 6 by 4 plus 2 by 4. And that is going to give us 24 plus 8, which is 32. And so we have 4 electrons left. Let's go ahead and place them on the I. Okay, so next up, we need to provide the steric number. As I said, the steric number is going to be equal to the number of bonding pairs around the central atom plus the number of lone pairs around the central atom. And so we have 1, 2, 3, 4 bonding pairs plus 1, 2 lone pairs. And so it has a steric number of 6. Next up, we just need to note down how many lone pairs we have. 2 lone pairs and 2 bonding pairs. And so now when we come to our VSEPR chart, we're going to go down to the steric number of 6. And so the basic geometry is going to be our electron geometry. And that's because it tells us the way that the electrons are distributed around our central atom. So it's going to be octahedral. But we also need to note the fact that there are 2 lone pairs. So it's molecular geometry, which is dependent on the bonding pairs you have around it, are going to account for those lone pairs, and so it's going to be square planar. And its steric number, the way to its notation that tells you how many bonding pairs you have compared to lone pairs would be AX4E2. So these are your bonding pairs and these are your lone pairs. And so now let's identify the bond angles and name the shape. And so back to your chart. So you would have I, the 2 lone pairs, and then behind you have a Cl, behind you have a Cl, in front another chlorine, in front another chlorine, okay, and so now we need to determine the angles. Yes, there is a lack of symmetry in what the axial groups are, because you do have 2 lone pairs, but the symmetry in the way that we optimize its arrangement to account for those lone pairs will allow it to have the typical bond angles and no bond distortion, because the effects would cancel out. So what that means is due to the, first let's think about angle. Usually if it was just one different group, that different group would cause a difference in the angle by causing extra repulsion or reduced. So because it's a lone pair, it's going to increase the repulsion, which would squeeze the other bonds. But in this scenario, the increased repulsion on this side is balanced out by the increased repulsion caused by these 2 lone electrons. And so that squishing effect would be balanced out on both the sides, leaving this angle as 90 degrees, as it should be, as well as this angle to the Cls also as 90 degrees due to the balanced pushing effect by the other lone pair of electrons. And so in terms of our angles, you will have the optimized angle of 90 degrees, and additionally, that would mean no distortion an angle due to the symmetry. Due to symmetry. Okay, next up we would like to find out about whether it's polar or non-polar. And so that also relates back to the symmetry here. We would have the dipole pointing towards the lone electrons, towards chlorine, towards chlorine, towards chlorine, and towards chlorine. So what's going to happen here are these two are going to cancel each other out, backwards, forward, which leaves these two. And in this case, we're lucky because the difference in electronegativity between the two lone electrons and iodine are the same. And so these two dipoles would exactly cancel each other out as they should. And so we're going to have a non-polar molecule. Okay, and that's it. Next up, we'd like to do IF5. So as usual, we count our valence electrons. 7 plus 5 by 7. And that is going to give us 42 electrons. So we're going to have I in the middle, because that makes the most sense, because we have more fluorines. And then we're just going to surround it with fluorine. Begin with single bonds. Fill in the valence of the fluorines. And then next up, we're going to see if we have anything left over. So we're going to have 6 by 5 plus 5 by 2. So the lone pairs and the bonding electrons. And so that is going to give us 30 plus 10, giving us 40. And so we're missing 2 electrons here. And so the best place to place them is on the central atom because we filled in the octets for the fluorines, leaving us with that. And so now that our valence electrons are all taken care of, we can check the formal charge. On the fluorines, we would have 7 minus 7, giving us 0. On the iodine, again, we're going to have 7 minus 2 lone pairs minus 10 in the bonding pairs over 2, and that is also going to give us 7 minus 7, and that's 0. So our formal charges make sense, and our valence electrons are taken care of, which means that this is the correct Lewis structure. And so now we go about getting the steric number. And so, as I said, it is the number of bonding pairs plus the number of lone pairs. Around the central atom, we have 5 bonding pairs and 1 lone pair, so we have a steric number of 6. To demonstrate or notate how many lone pairs and bonding pairs we would have AX5E. So 5 bonding pairs and 1 lone pair. Next up, using its steric number, we go about finding its electron geometry. So we'd come down here to the 5, and the electron geometry is going to be trigonal bipyramidal. And its molecular geometry is now going to account for the fact that one of them is a lone pair. So its molecular geometry would be seesaw or sawhorse. So just come to the steric number and then begin going right depending on the lone pairs. We have 1 lone pair, so we stop here. So now let's sketch out what it should look like. So we have I in the middle, its lone pair here, F, F, and then let's fill in fluorine's valence octet, sorry. Okay, now in the optimized trigonal bipyramidal structure, the angles here are 180 and the angles here are 90, but that is fully dependent on all of these groups being the exact same, so that the electron repulsion can be minimized by an equal/equidistant separation between each of them. And so that is why you'd have specific angles between those going in and out of the screen. So these ones all have an angle of 120 between them, and the same angle between those that are on the plane. So here we'd have an angle of 90. But because of these two lone pairs of electrons, they're actually going to push the rest more. And unlike the case before where that push is balanced out by the exact same push in the opposite direction, canceling it out, that's not going to happen. So it will cause a distortion where this angle will be over the 90 degrees, which means that the angle between this fluorine and these ones that are in and out of the plane will actually be less than the idealized 90 degrees, because this is pushing extra on both of these fluorines, kind of squeezing them. And then additionally, because of this lone pair, it's going to cause these three to no longer be equidistant, and it's going to squeeze this angle to be over 120, which is going to make this angle under 120 degrees. And so we would have bond angles of between our fluorines under 90 degrees and under 120 degrees. And we would have distortion due to lack of symmetry. Okay, and then now we want to find out whether it's polar or non-polar. And so we begin by drawing our dipoles. We would have this one pointing up, this one pointing down, so these two would cancel. This one pointing this way, this one pointing this way, and this one pointing this way. Now, if this was another fluorine, these two angular components in these two dipoles would cancel, only leaving one in the opposite direction, which would be exactly equal to this one. But in this scenario, that's not the case. This isn't fluorine. So these two dipoles will be non-equal and not completely cancel. And so we're going to have a dipole moment that is non-zero, which means that we will have a polar molecule for both of them. And that's your final answer for this one.